Dear conference organizers and participants, it's my great honor to report my work here. My name is Deng Liang from Uniper's BERT team. Here, Unipers is the domain name of my company, Waiyan Online Digital Technology. As the technical leader of algorithm team, I led my colleagues and interns to participate in this competition. And fortunately, we have achieved decent results. We got the first place at a correction top 1 task and the second place at a correction top 3. Also, we got the second place at a detection task. And in this slide, I want to take a few seconds to share photos of my coworkers and to express my gratitude for them. My report will be conducted in 3 steps. First, I'll introduce how we design our system. In the second step, we'll discuss how to implement the models required by our system. Since we have a total of 3 types of models, we need to integrate the results. So, we choose voting strategy. Finally, we will analyze the results. For system design, we will discuss some model structures and techniques commonly used in the field of English grammar error correction, and then apply these models to the CGED task. In the CGED, we have 6 evaluation dimensions. Generally, detection, identification, and precision can be obtained through GED or grammar error detection, while correction top 1 and top 3 should be obtained through GEC or grammar error correction. For GED, the most common method is sequence tagging, while with the emergence of pre-trained language models represented by BERT, many studies have proved that the effect of the BERT-based sequence tagging model exceeds models like CRF and LSTM. So it's very natural that we let a BERT-based sequence tagging model to do GED task. For GC, the most powerful method is using sequence-to-sequence techniques. Often we call it machine translation. In this slide, we can see very clearly that advances in machine translation always promote the development of GC field. For example, in 2017, the transformer structure was proposed by this paper, Attention to Oil Lead, and then applied to GEC in 2018. In 2020, a novel strategy called BERT fuse model was proposed in this paper, incorporating BERT into neural machine translation. And in the same year, this strategy was applied to the English GEC task and achieved state-of-the-art results. And let's see the F0.5 score of these GEC models on the most popular GEC benchmark local test set. It's obvious that GEC always benefits from advances in machine translation. So, in order to build a better system for Chinese GEC task, we should try to use the most advanced machine translation network structure. Up to now, the best AMT model structure is the transformer and BERT fuse. Based on the above knowledge, we design our system for CGED as follows. First, we use BERT-based sequence tagging models for GED. We call it precision tagging model. Second, for GC task, we use the state-of-the-art AMT model, including transformer and BERT fuse. Here I list 2 state-of-the-art work in 2019 and 2020. In the first paper, transformer structure was adapted to train an AMT model and synthetic data was added to relieve data sparsity. In the second paper, BERT fuse structure was adopted and achieved good results. As can be seen from this table, researchers from Chinese GEC field only have about 0.8 million allocated sentence pairs, while researchers in English GEC field can obtain about 5.4 billion sentence pairs. So Data sparsity problem is much more severe in Chinese GEC task, so we add sensitive data to relieve data sparsity. And this year, 6 months ago, authors from Grammatical proposed a sequence tagging model for GEC called GECter, and achieved the state-of-art result in English GEC field. So we designed a sequence tagging model based on BERT in our system. We call it correction tagging model. Finally, we use voting strategy to merge results from different models. Let's take a further look at our system. The system contains 4 types of models, each of which has one or more single models. Here in the first row, we use sequence tagging model for GED, and we call it position tagging models. And in the second row, we use sequence tagging model for GEC. The model structure is similar to GECter proposed by Grammatical. In the third and fourth row, we use AMT models, transformer and BERT fields respectively. We add synthetic data to ensure our AMT models. It should be noted that for the convenience of description, AMT models based on pure transformer was regarded as one of the BERT AMT models in our CGD tech report. Then I'll give further introduction about 3 types of models in our system: the position tagging models, correction tagging models, and BERT-fused AMT models. The position tagging model is a simple sequence tagging model with a Roberta encoder. The model concentrates on the error localization task. The output label consists of 8 types of tags and indicates the start pose and end pose of each error for the input sentence. And then let's come to the correction tagging model, or the GEC sequence tagging model. It's an encoder made up of pre-trained BERT-like transformers stacked with 2 linear layers with softmax layers on the top. The output of the model contains about 9,000 types of tags. Here, the tags review the editing operations for each Chinese character, including keep, delete, append, and replace. For a sentence pair like this, source sentence is 突然风起来刮了. Target sentence is 突然刮起风来了. We align the source tokens with the target tokens and collect the added steps. An append tag is like this: the word append followed by a short line and a Chinese character. So we have about 4,000 append tags in total, and can cover most append operations in our corpus. The number of replace tags is about 5,000 in total. Now let's talk about the BERT-fused model. The BERT-fused model is originally proposed for AMT task in the paper below, and we transfer it to our correction task. Due to time limitation, we won't explain too much about how it works. In simple terms, this model can be divided into 3 parts as shown in the left part in the figure. It is BERT module. The BERT module is nothing but a pre-trained BERT model. Its parameters are fixed during the whole training process. The BERT module extracts rich representations for an input sentence, input sequence, and then the representations are fused with each layer of the encoder and decoder through attention mechanism. In the figure, if the BERT module, the BERT encoder attention block in encoder layers and a BERT decoder attention block in decoder layers, along with the red lines, are all removed from the figure. Let's see. And then the rest part of the figure is the normal transformer structure. We call this transformer structure transformer module. So a BERT-fused model can be divided into three modules: the transformer module, the BERT transformer attention module, and the BERT module. And the initialization of the transformer module is tricky. We should first train a transformer model on the Chinese DEC data from scratch until it converges, and then we copy the weights of the transformer model to the transformer module of the BERT-fused model. For the BERT encoder attention blocks and BERT decoder attention blocks, their weights can be initialized randomly. And now let's talk about the synthetic data. To address the low resource problem, we generate a huge amount of artificial data. We collected 60 million error-free Chinese sentences from multiple sources, and we perform word-level operations and character-level operations to introduce synthetic errors into these error-free sentences. Take word-level operations as an example. For word-level operations, including substitution, deletion, insertion, and transposition, is performed with distinct probabilities, which simulates the proportions of S, M, R, and W errors in the CGED dataset. And in this slide, we give some examples. And we use voting strategy to merge the result of different types of models. Our voting strategy is inspired by Alibaba's solution in CGED 2018, and we explain it to you through this picture. As you can see, the output of precision tagging models provide the precision and the type of each error, but lack corrections for S and M errors. And the output of BERT-fused AMT models and correction tagging models are corrected sentences. We convert the output sentences into edits using an alignment tool we developed. In the detection stage, we collect all edits and then vote to determine the detection result. We accept an error proposal only if it gets the votes more than a threshold. In this example, we set the threshold to 6. And then only the edit 78S is kept. Then, in the correction stage, we add candidate words to the detection result. In this example, the candidate word is 没有. And finally, let's come to the result analysis. Here, we made a detailed table about correction top 1 evaluation of our models using our own evaluation tool. And these F1 scores calculated by our script will be slightly different from the official script. This table is discussed in detail in our CGED tag report. Here I just list my conclusions, but I won't explain too much. Firstly, we can see that our two best single models are Model 8 and Model 12. Model 8 and Model 12. We can see they are all BERT-fused models. This shows that the most powerful GEC model method is BERT-fused AMT models. What's more, if we compare Model 6 with Model 7, we can see a huge improvement in F1 score while both of them use the same amount of manually labeled data as training set. In my opinion, BERT-fused model performs well in overcoming data sparsity. Secondly, CGED task can benefit from synthetic data.